Welcome to qnawire.
Hi. So we are given a problem of parallel plate capacitor. So we have an air capacitor which is made by two metal plates, each having area A and are separated by distance t. So let me draw the metal plates here. So we have two parallel metal plates with each having area of A, and these two metal plates are separated by distance t. Now it's given that in between the two metal plates, a metal slab of thickness A, which is less than D, is inserted. So we have a metal slab of thickness A. This thickness is less than the separation D, and it is inserted in between the two plates. And in the first part of the problem, we need to find the net capacitance of this arrangement. Now note that in between the two parallel plates, so in between these two plates, we have a metal slab inserted. So this is a metal slab and not a dielectric slab. That is why this arrangement is like an arrangement of two capacitors connected in series. So we have a capacitor consisting of the upper. So let me write it like this. So we have a capacitor consisting of the upper plate and the metal slab. So let's call this capacitor C1. And then we have another capacitor consisting of the middle metal slab and the lower plate. So this is capacitor C2, which is filled with air. So these two capacitors are filled with air, and the distance, as you can see, between the upper plate and the metal slab and the lower plate, let's call this distance be d prime, and for both the capacitors the distance is same. And if you'll see, the distance d prime is going to be equal to, so total distance, which is d minus the distance where we have the metal slab, so the thickness of the metal slab, which is A, divided by 2. So this is the thickness or the distance between the two capacitors, T prime. Now, having found that, so in the first part of the problem, we need to find the equivalent capacitance of this arrangement of two capacitors, which are in series. So the equivalent capacitance can be written as 1 over C equals, since it's like a series combination, so 1 over C equals 1 over C1 plus 1 over C2. Now note that C1 and C2, they are separated by the same distance, so, and they have the same area. So C1 is indeed equals to C2, which is equal to epsilon naught A divided by the distance, which we have already calculated here, d prime, which is d minus A all divided by 2. So that's C1 and C2. Now, since C1 is equal to C2, which is going to imply the capacitance C is nothing but it's going to be equal to half times C1. So the equivalent capacitance is half of C1, and we have already calculated C1, which is equal to C2. Yeah. So from this, we find that the equivalent capacitance for this combination is going to be epsilon naught A divided by D minus A. So this is the answer for the first part of the problem, where the equivalent capacitance of this combination is given by epsilon naught A over D minus A. Now moving to the second part of the problem, where we need to express this capacitance C in terms of the capacitance of this combination in which we do not have the metal slab in between the two parallel plates of the capacitor. So if we only have the two parallel capacitors like this, and if we do not have a metal slab in between the two capacitor, again they are separated by distance d. So in that case, the capacitance, let's call this C naught, is going to be simple, like C naught. So this is so we can use the formula for parallel capacitor separated by distance t, each plate having area A. So for this we have epsilon naught A over D. So this is our C naught. So this is the part B of the problem. And since we already calculated the equivalent capacitance of this combination as epsilon naught A over D minus A. So I'm going to write here C equals, which is the equivalent capacitance, equals epsilon naught A over D minus A. Now I need to express this C in terms of C naught. How do I do that? So I'm going to do a little bit of algebra here. So I can rewrite this as this. So epsilon naught A, I'm going to multiply and divide by D. So I've multiplied by D here. So divided by D, I'm going to multiply by D. So this expression and this expression, they are equivalent, and which indeed gives me, so I have C equals, so epsilon naught A over D is nothing but C naught, and I have this term here times D divided by D minus A. And sorry, this is the answer for the second part of the problem. So the equivalent capacitance C equals the capacitance when we do not have the metal slab, which is C naught, times D over D minus A. And moving to the third part of the problem. So in third part of the problem, we need to discuss what happens to the capacitance in the limit A tends to 0 and A tends to D. So let me write the net capacitance C. So the net capacitance of the combination, let's write in these terms, in terms of C naught. So C equals C naught times D divided by D minus A. So we need to find what happens to the net capacitance in the limits A tends to 0 and A tends to D. Now, as you can see, as A tends to 0, so from the above expression, when A tends to 0, we see that the net capacitance becomes C equals C naught. So when the thickness of the metal slab tends to 0, so we have the net capacitance equal to the capacitance in the case where we do not have the metal slab. So C equals C naught. And when A tends to D, so in the above expression, if you put A tends to D, A equals to D, you will find that we are going to have C naught times D divided by 0, which is nothing but like it is infinity. So we have when A tends to D, C tends to infinity. So that means when the thickness of the metal slab becomes D, the distance between the slab, so the capacitance C tends to infinity. So these are the two conditions, and with this we finish the problem.